Hello everyone, and welcome to another lecture with Mount San Antonio College. And this lecture is going to be on welding electrodes. And so I have a sample of a welding electrode. Now typically these are about 14 inches in length. However, they do vary from about 9 to about 18, depending on the diameter of the solid wire that's used for the electrode. This wire is solid, that's in the center of this electrode. It is solid. And then you can see the coating on the outside of the electrode itself. The other thing to mark on, or take a notice, is that you see these markings on the flux itself. Those are markings from the manufacturer. But also here you see the markings of the electrode itself, where it says Excalibur 7018 H4R. And that 7018 is the number that we're going to be talking about today, with the markings on the electrode itself. This is the manufacturer, and that H4R has to do with, because this is a low hydrogen electrode, which we're going to be talking about in just a moment, it's actually moisture resistant. They're guaranteeing the amount of moisture that this electrode can absorb or will absorb. Okay, so this is just a typical welding electrode, and just wanted to give you some history of the welding electrodes. Arc welding wasn't really started until around 1881, so it was quite a bit ago. And when they first started out, they were just using a bare wire. A guy by the name of Slavinoff, it was his method. So they were just taking a bare wire, if you will, one of these electrodes with no flux on it, and they were welding with it. The issue with that is that in our breathing atmosphere we have 78% nitrogen and 21% oxygen. So the nitrides and the oxides that are actually in our breathing air was actually attacking the actual molten puddle. And so you were getting contamination of nitrides and oxides into the molten metal. Well, eventually they dipped it in lime. They've given no credit to the gentleman that or woman that found that, but one way or another, they dipped it in lime and they found out that they were getting a little bit better quality welds from it. Well, that went on for a bit with the lime coating and the improving of the weldability of it, until Kajelberg came along, and he found the coated wire. And for the most part, it's the same method that we're using nowadays. Sometimes the coating on the electrode is extruded onto it, and sometimes they use a dipping method where they take the bare wire and actually dip it into a bath of the flux coating itself. But that coating on the outside is used for a number of things. Namely, as this coating burns on the outside of the bare electrode, it releases an inert gaseous atmosphere, and it protects the molten puddle from the nitrides and the oxides that I was talking about earlier. It also improves weld appearance. It's easier to strike the arc. You have a depth of penetration control, and you can produce X-ray quality welds. The other thing that it does is, not only is it, while it's burning and protecting the atmosphere from the nitrides and the oxides, but the residue that's left over from this flux is called slag. And that slag protects the nitrides and the oxides while the molten puddle itself is cooling. It protects it from the atmosphere, so you don't get that contamination. It also slows down the cooling process itself. And has the ability to lessen it cooling very quickly. So one of the things I wanted to talk about was striking of the arc. If you've ever taken a bare electrode, in other words, just break all the flux off this and try striking it, try running it, because that's the way it was in the early days when they first started trying to do this. Obviously, they had a lot of contamination with the nitrides and the oxides, but just try doing it. It's not the easiest thing to do. And then certainly with the With the coating on the wire, it became a lot easier to strike the weld and maintain the quality part of that. The American Welding Society didn't really start until 1919, so it was a few years after this, and they started putting together rules and regulations of the welding industry. And what's important to note about that is that no standards existed till around 1940. So it was almost 50, 60 years later that we started establishing standards. And since 1940, the American Welding Society has developed specifications for filler metals to cover welding of carbon, alloyed steels, stainless steels, copper and copper-based alloys, aluminum alloys. What I want to say is that through these specs, the user is informed that a certain electrode can produce a weld having specific mechanical properties. And that's the important part of this, that they can show that if you use this electrode and you use it on this particular type of material, you are going to end up with this particular type of mechanical properties. And that's where the engineering part of this enters into play, where you can weld a building together, or you can weld metals together, and you can have a live load, meaning people and everything that's live, and a dead load, where you have desks and books, bookcases, things of that weight. And you are going to have a certain mechanical property for that finished weld. I talked to you about, prior to coated electrode, the atmospheric gases formed nitrides and oxides in the weld, and it left a very brittle, a very low tensile strength weld. And with the coated electrode, that provides an automatic cleansing and also deoxidizing action of the weld metal itself. Okay, a few things on the electrodes. First off, I just wanted to this is one of the handouts that we have, and I don't know with the glare if you can even see this, but you can see in the old days they used to have what's called group colors and spot color, and there was an end color on the electrode. This is the old method of marking the electrodes. Nowadays, the newer method, they just stamp the number right on the electrode itself. What's amazing to me is that I was actually on a building. I was in late part of 1980s. I was on a building, and it was an old-time welder, and he actually remembered the group and the spot colors and the end colors for a 7018 electrode, which is a low hydrogen electrode. So he told me the colors, and I recall going out to my truck, and I was looking up the colors, and he was right. He's the only person I ever met that was part of the older method of markings of electrodes. Of course, nowadays, they just stamp the numbers on the electrode itself and make it a lot easier for us to identify what kind of electrode that we're working with. The electrode sizes are from 1/16 to 5/16. 1/16 you're at about 40 amps, and 5/16 you're at about 400 amps. And I did my best here to try to kind of draw the electrode where you have this solid core wire right here, and then on the outside of it is the actual flux itself, coating on the electrode. But in addition to that, you have a number that's stamped on this. And I wanted to take just a moment and talk to you about the numbers, the markings on the electrode itself. The way we do this is we always leave the last two numbers. So even if this was a 118 electrode, we would leave the last two numbers, but you key in on the numbers that are left, or in this case, it's a 70. And what they're guaranteeing is that your completed weld, after you've welded, you're guaranteed to have 70,000 pounds per square inch of tensile strength. And what that means is that as you have a finished weld and you try to pull that piece apart from what you just joined, it would take 70,000 pounds per square inch to actually pull it apart. And what I'm here to suggest to you is that you can make a weld 1 inch by 1 inch on a piece of metal, 1 inch by 1 inch, and you would be able to pick a Cadillac up or a vehicle up with that at 70,000 pounds per square inch. So that kind of gives you an idea of the amount of strength that you get on a completed weld. The next number after that is the position, this 1 here, and 1 indicates all positions. If it's a 2, it's flat and horizontal fillet welds only, and a 3 would indicate flat position only in the flat position. So in this case we have a 1, so we can weld this in all positions. And the positions are clearly marked on this handout for this lecture, where it states that a 1 is all positions, flat, vertical, overhead. A 2 is flat and horizontal fillet welds only, and a 3 is flat positions only. As an inspector, why is that important? Well, if I walk up to someone and someone's using a 70-24 electrode with a 2, they should not be welding in the vertical position with that, because it's a flat and horizontal fillet weld only position electrode. So that's where the importance of, there's certain electrodes you can weld in all positions, and others you can only use in flat and horizontal and or just in the flat position itself. The last digit happens to be a very informative digit. It gives you a lot of information. It gives you the polarity, the amount of penetration, and the coating, the type of coating that you have on the electrode. So let's talk about that for just a moment. Again, I don't know how well the glare is going to be, but I'm going to make an attempt. But these are the last digits on the electrode. And it tells you what kind of coating is on the electrode. It also tells you what kind of polarity you can use for that electrode. And it gives penetration that this electrode gives, and also the manipulation. That there's only a couple oscillating electrodes. Most of them are dragging electrodes. However, these two are important items: what kind of coating it is and what kind of polarity. And we're going to talk more of polarity and of the coatings here in just one moment. This last digit right here, that last digit, if it ends with a 5, a 6, or an 8, it's a low hydrogen electrode. Okay, we typically use low hydrogen electrodes when we're dealing with high sulfur and high carbon steels. It reduces, what we know in the industry is that hydrogen causes cracks. And of course, moisture is H2O, hydrogen and oxygen. So we don't want hydrogen into the weld. And especially with high sulfur and high carbon steels, we go with low hydrogen electrodes. That means that you're guaranteed that the electrode is low hydrogen. And there's ways that we maintain that low hydrogen amount. But the importance of this is that the engineers saw that, caught on to it, and I can tell you the majority of the electrodes, quite a bit in the industry, is all low hydrogen electrodes, because they like that possibility of reducing the possibility of having hydrogen being entrapped into the weld and it causing cracks. Whether it's high carbon or high sulfur, it's used quite a bit throughout the industry. Something to know about the low hydrogen electrodes. One is that when you open up a solid hermetically sealed container of low hydrogen, it falls into this category. And the 70 series electrode can only be exposed to the atmosphere for 4 hours before it has to go into a heated rod oven. An 80 series electrode can only be exposed for 2 hours 90 series electrode, 1 hour, 100 series electrode, a half an hour, and it's 110 series is a half an hour. It never goes less than a half an hour. But when I say it needs to go to a heated rod oven, I'm talking about 250 degrees Fahrenheit storage oven. So it's not uncommon if you're dealing with low hydrogen electrodes to have a portable rod oven. They're called Phoenix, is one of the manufacturers that makes them, but there's other brands out there, where you would put the electrodes into this heated storage container and then bring it to wherever you're going and plug it in so that the electrodes would never be exposed more than this time frame right here in order to maintain the low hydrogen characteristic of it. Keep in mind, when you get these low hydrogen electrodes, they're hot, 250 degrees Fahrenheit. And what I'm trying to suggest to you is that if I took a bundle of low hydrogen electrodes out of the oven and put them in my glove, it wouldn't take much time before I'd have to set them down and get my hand out of the glove itself. So they're going to be hot when you get them. When I worked at the nuclear plant, we used to issue out rod ovens to everyone that had low hydrogen electrodes. So we would give them to them hot in the oven, and then they would transport those electrodes to wherever they're at and then plug the rod oven in once they get where they're going. So those are if the number on the electrode is a 5, a 6, or an 8, you need to know that it's a low hydrogen electrode and that it needs to be in a storage rod oven. It needs to be heated. If the last number is a 4, a 7, or an 8, it has iron powder in it, meaning that there's iron powder in the coating of the electrode. And one of the important things about having an iron powder is that iron powder adds metal to the actual weld deposit, and you end up with a high deposit rate. It also gives it a very pleasing appearance. What I'm trying to say is that if the electrode ends with a 4, a 7, or an 8, there's actual iron powder in the coating. So when you go to weld, the iron powder becomes part of the weld metal. The reason why you have a high deposit rate or a high deposition rate is because any other electrode that doesn't have iron powder in it might go this length. But if it's an iron powder electrode, because the iron becomes part of the weld metal, you would be getting additional length with it. That iron powder in the coating gives it a very pleasing appearance. So anyone that runs iron powder electrodes, you can see in the finish, it's a very nice, very smooth looking finished weld. Some engineers like that particular finish. Also, they want the deposit rate. They want more weld being placed. Now, because there's additional iron powder in the coating, you have to increase the amperage. So what I'm trying to suggest is that if I had a welding electrode without iron powder, I might use 120 amps. But that same size electrode, 1/8 inch, that has iron powder, instead of 120 amps, I might be running 165 or 175 amps. So you have to increase the amperage because of the iron powder itself. Even though it's the same size solid core wire in the same center of the electrode, because of the iron powder, the amperage is increased. Now, you might have noticed there is an electrode that has both iron powder and low hydrogen, and that's the one that ends with an 8, which happens to be the one that I was showing you earlier, 7018, and it's the one that I'm demonstrating on. So this electrode uses more amperage, and also it's a low hydrogen electrode. And I would suffice to say that this is the most common electrode that's used in the welding industry itself, is 7018. Most people, when they run arc welding, run 7018 electrode, although there's quite an array of electrodes out in the industry, including stainless electrodes, copper, the Manel electrodes, aluminum electrodes and such and so forth. So there's quite a bit of different types of electrodes. And I think that was about it that I wanted to say on this part of the screen. Also, at this time, I wanted to just talk about two other items. So let's take just a moment and talk about polarity and the knowledge of polarity. And I'm taking a chance again to see whether or not you can see this handout. But when we're dealing with DC plus polarity, we always go by the electrode, where the electrode is. So if the electrode, and there's the electrode holder, if it goes back to the machine to the positive terminal, you're on DC plus polarity. Here's DC minus. And if you follow the polarity from the electrode and it goes back to the negative polarity on the welding machine, you're welding on DC minus. And then, of course, we have alternating current where it wouldn't matter which one you're hooked up to. It's literally 50-50. Half the time it's DC plus and half the time it's DC minus on the polarities. So those are the three polarities on the electrode. All right, so why might that be important? Well, here's a for instance. This common electrode that I was talking to you about earlier on at the beginning of this lecture is a 7018 electrode. And this electrode can only be ran on alternating current and DC plus. So you cannot run this electrode on DC minus. And I've found that in the industry where someone is welding 7018 and I go back to the welding machine and they're hooked up to the negative terminal. And that being the case, that means that their work is non-certified. It needs to be removed. And that's exactly what we did. I went and got the superintendent. I told them to, they can either air arc it out, they can either grind it out, but all the welding that was done on the wrong polarity had to be removed. This particular electrode, when it's ran on the wrong polarity on DC minus, it makes like a spitting sound. It's a very, I know it right away. It's like it's spitting at the weld itself. And it tells me that the welder's welding on the wrong polarity. So I would follow the lead all the way back to the welding machine and verify that in fact it's the wrong polarity, and then I would notify the foreman or the superintendent of the weld crew. So we want to be aware, we want to know what polarity that we're working on, and this particular handout tells you what polarities, that last digit, what polarities you can use that electrode for. So just to kind of grasp it one more time, the polarity goes by what the electrode is. So if the electrode is hooked up to the positive terminal on the weld machine, if it's hooked up to the positive terminal, you're on DC plus, direct current positive. You're on DC plus. And of course, the ground would be hooked up to the negative in DC plus mode. However, if I switch these, which I could easily do, and take the electrode to the negative terminal, and then hook the ground to the workbench, if you will, or work plate, in this case, it would be DC minus. I would be on DC minus polarity. The other thing is, on the machines, there's a flip lever there, and if you put it on alternating current, it wouldn't be one or the other. It would be alternating current, like this, and it would be half the time positive, half the time negative. In other words, the electrode would be half the time positive, half the time negative. That's alternating current. Right here, alternating current AC. Well, let me at least tell you this. Alternating current isn't used much in the industry. Almost very rarely, unless you just have a machine that's all it does is produce alternating current. Most people in the industry use DC plus, meaning that the electrode is hooked up to the positive terminal, and the work piece itself would be minus. Most people use DC plus in the industry itself. Now, why might you say that the polarities are important of what I just talked to you about? Here's the key. 2/3 of the heat is on the positive terminal. 2/3 of the heat is on the positive terminal. 1/3 of the heat is on the negative terminal. So what I'm trying to tell you is that if this electrode is, in this case, it's DC positive, if the electrode, which is hooked up to the positive terminal, and we're DC plus, that means that 2/3 of the heat is on the electrode, which means more penetration. And of course, if you're welding something, most of the time you would prefer the highest penetration if you could. However, there are times when you're welding thin materials and you don't want that 2/3 extra, 2/3 heat into the weld piece itself. In that case, you would switch over into DC minus, where only 1/3 of the heat would be on this. Of course, these would have to switch also. So the electrode in this case would be minus, and the workpiece would be positive. So in this case, 1/3 of the heat would be on the electrode, where you would weld thinner materials. What I'm trying to tell you is that if I had a thinner piece of material and I switched it over to DC plus, didn't change the amperage at all, just switched it over to DC plus, and I took my electrode that can run on all polarities, and I tried to weld that thin piece of material, it would go right through it, because 2/3 of the heat would be on that thinner material. Then if I just switch the polarity over to DC minus and use that same setup and try to weld the thin material, it would weld it just fine, because I would only be welding with 1/3 on the negative terminal. So that's the theory behind it. However, I just want to give you some practical knowledge. Only if I'm welding thin materials would I be on DC minus. And in almost 40 years that I've been welding, I've probably switched it over probably less than that in all the years of everything I've been welding. Now, I would say that if I was in a shop and that's all I was welding was thin materials, of course I'd be spending a lot more time on DC minus. But the most of the time when I was welding, it was structural welding. And so I was using the DC plus polarity. And the last thing that I wanted to talk to you about for the electrodes is magnetic interference, sometimes called arc blow. The magnetic interference when you're welding on a plate, the electrode has a magnetic field, this electrode, and it's circular going around this electrode. It's in a circular pattern. On your weld plate that you're welding, the magnetic fields on the ends are oblong until they get a little bit further out into the plate, then they become circular. And what I'm trying to say is that the circular magnetic pattern on this electrode, once it gets away from the edge of the plate, they don't interfere with each other, and you're able to weld with no problems throughout the plate. Until you start getting towards the end, it starts getting oblong again. And that's where we get this magnetic interference. There's a couple different ways to help a person with the magnetic interference. Of course, the old terms, people used to say, oh, just go to AC current, go to alternating current because half the time it's 50% positive, half the time it's negative. And they're right, it would cut back on the magnetic interference. It's just in the field, we wouldn't normally switch over to AC current. So you have to learn how to move the electrode to offset the arc flow. And the correct term, you don't get much magnetic interference in the beginning. However, when you get towards the end of the weld, that's where it really becomes more magnified. This is much more magnified than the beginning of it. But as you get towards the end of the weld, what you would do is you would bring the electrode in towards the plate, in towards your body, if you will, and bring it inward, the head of this towards me, in order to control that magnetic arc flow towards the end of the plate. And that's a very, very common way to offset that. Also, you can connect the ground directly to it. Some people put jumpers on these, and they've noticed a difference in the arc flow in helping them, where they'll have like a 1 or 2 foot jumper with clamps. If I'm welding in the vertical position, if I'm welding a plate here, literally, I would start out welding, I would be doing just fine, and then about right here, I start getting a lot of that magnetic interference known as arc flow. And what I would end up doing is having to lower the electrode down in order to maintain and control of this. I've had so much arc flow in the past of this interference that literally the electrode is almost vertical. I'm almost in this position as I'm finishing the weld. What I want to say to you is that it's not something to be nervous about. It's not something to be anxious about. When you've done this a number of times as you're moving and you see the arc flow happening, this interference, all you have to do is lower the electrode down and just slowly continue. You don't speed up at all. None whatsoever. Just stay, watch the weld puddle itself, make sure that it's established, everything is exactly how you want, and then finish the weld and complete it. So you'll see some of that as we get into the arc welding and we start welding in the flat and horizontal positions, that when you run into this magnetic interference at the end of the plate, move the electrode inward and it will help you with that. So I think that's about it. This is what I wanted to cover with this electrode lecture, and we'll see you at the welding building of Mount San Antonio College.